Hello and welcome again to another review session for Calculus 3208 for your final exam, presented by CDLI. Today we're talking further about derivatives and computation of derivatives. Specifically, we're going to talk about the product rule. And for the product rule, we're going to look at sort of where it comes from and how we make use of it. So let's get started. So today we're talking about a few different details about the product rule. So we're going to look at how it's derived, although we're going to kind of skim through that a little bit and we'll talk about why. Then we're going to talk about how we use the product rule in algebraic context, which is by far the most common way that we make use of this thing. And then we're also going to look at it in a numerical / graphing context as well. See how that works. Alrighty. So first off, we have a derivation of the product rule. So the product rule is derived basically by starting with a general function p of x, that's the product of two others, f times g. And we've already seen in previous sessions and in your course how you differentiate a sum using our sum rule or a difference using the difference rule. And there are lots of details with those things. But they are fairly straightforward. The product rule is the first one that we come across. When we have to differentiate a product, the algebra gets a lot more complicated. So what you can see here is that I've written out a full derivation, which is really a proof of the product rule, using the definition of the derivative. So if we look at the definition of the derivative for any function p of x, it would look like that. And then I just sort of split the function p of x into f of x times g of x. And then there's just one little trick that we play with that. And the one little trick that we play with that is we sort of add and subtract something at the same time to what we have. So this bit here on the end and this bit here at the very beginning is the same thing that we had in the previous line. And then you'll notice that here in the middle, I've subtracted this f of x plus h times g and added it at the same time. That's an old algebra trick that we sometimes use. When we want to get something, a new component of our equation, but we don't want to change the value of what we're doing on one side of the equation. So by adding and subtracting, we're really just adding 0, so it doesn't change the value. But what that allows us to do is if we now take the first two terms that we see there, remove a common factor of f of x plus h, and then in the last two terms that we see down here, we remove a common factor of g of x, well, what that does is it allows us to separate or break up our limit into the sum of two separate limits now, right here. So this one and this one by simply making this fraction that we started with into two fractions with that same denominator of h. And we remember our limit laws say that the limit of a sum is the same as the sum of the limits. So we can do that. And then if we evaluate each of those two limits independently, what we end up with is a formula that looks like f of x times g prime of x plus g of x times f prime of x. Now there are lots of different ways we can write this out. But basically, what all this tells us is that if I want to differentiate a function p, that's the product of two other functions, f and g. Now, lots of folks write this differently than I do, but I usually think of it as the derivative of the first function involved in my product multiplied by the second function plus the derivative of the second function multiplied by the first function. So that's f prime g plus g prime f. Okay? And I usually just say the derivative of the first times the second plus the derivative of the second times the first. So let's see how we put that into action. So here's a couple of examples here. We have, in the first case, a really ugly looking function because we have a quintic polynomial multiplied by a cubic polynomial. So if I were to try to expand this and write it all out so that I had all the terms so that I could differentiate them individually as if I were just using my power rule and my sum and difference rules for polynomials, I'd end up with 15 terms here before I even started to collect like terms. So if I just want to find the derivative quickly without doing a whole lot of simplification for this, I can write dy by dx is equal to, and I'll use the product rule. So I take the first bit there. So I'm just going to highlight the first bit in yellow. So I'm going to take the derivative of this first bit, and in order to do that, I'll just use my power rule combined with sum and difference rules for polynomials. So I get 15 x to the power 4 minus 8x plus, it looks like 15x squared plus 2x plus 7. Okay, and so that's the derivative of my first part. Now I'm going to multiply that by the second part without changing anything because I don't differentiate the second part for my first term. just the first part. So I have 15x cubed minus 3x squared plus 8. So what I've done is I've taken the derivative of the first multiplied by the second. Now I'm going to add to that the derivative of the second bit. So I'm going to write this down below here because this can be quite lengthy when the polynomials are complicated. So 15x cubed, I'm now going to differentiate the second part and then multiply by the first part. So let's say we highlight the second part of this, but we'll use a slightly different color here. Let's go with a green highlighter for that one. So, oh, that one didn't show up very well. So there's my green highlighter. And what I'm going to do now is say the derivative of that part is 3 times 15, which is 45. And then that's x squared minus 6x. And then I got to multiply all that by my first part again. So you'll forgive my sloppy notation here. I'm just going to write it down there to give myself a little extra space. So that's 3x to the power of 5 minus 2x to the power of 4, 5x cubed, x squared, 7x minus 9. Now typically the rule that we use when we are doing these things is we say after you take a derivative, make any obvious simplifications. For this one, there's lots of things that we could do to simplify this, but it would kind of defeat the purpose of not expanding it all out in the first place and using the product rule. So for this one, we're going to leave that as our simplified form and say that that's simplified enough for us. If we had to fill in a value for x and get a value of the derivative, we could do so with that. All right, so let's tackle the second one now. So we also want to take a derivative here, and this one looks a little bit messier. So before I get started with this, I'm going to rewrite all of these terms so that it at least looks like a polynomial. Okay, so in my first set of parentheses or brackets there, I have 3 times the cube root of x, so we'll call that 3x to the power 1/3. And then plus 3 over x to the power 7, so we'll call that 3x to the power of negative 7. And then we'll multiply by 10 over the square root of x is 10x to the power of minus a half. And then we'll subtract 15x cubed. So what we have there is just a rewrite, sort of the function f of x. So now we'll start looking at its derivative. So f prime of x now. So again, we'll use the product rule. We'll take the derivative of the first multiplied by the second to start with. So the derivative of the first factor there is going to be 1/3 times 3, so that's just x, and the exponent will be minus 2/3. So I've got x to the minus 2/3 for this bit when I differentiate, minus 3 7s are 21, x to the power of negative 8. Okay, so what I've done there is I've just differentiated this portion right there. And now I'm going to multiply by the second part. So this stuff over here, without taking any derivatives now, we have 10x to the power of minus a half minus 15x cubed. So that's the first term in my product rule, f prime g, or the derivative of the first times the second. I'm going to add the derivative of the second bit now. So 1/2 of 10 is 5, but we're negative here, so we have minus 5x to the power of negative 3/2. And we're going to multiply that by the derivative, or sorry, we're going to subtract the derivative of 15x cubed, so that's minus 45x squared. And all that has to get multiplied by the the first term, first factor I should say, which is not going to be differentiated at this stage. And we add to that 3x to the power of minus 7. So there we have it. That's all expanded out using product rule. Now if you wanted to simplify this a little bit, and I would usually require that my students don't leave any fractional or negative exponents at the very least. So this would be 1 over the cube root of x squared minus 21 over x to the power of 8 multiplied by 10 over the square root of x minus 15x cubed. And then for the next term, what I'm going to do is I'm going to factor out both of those negatives. So I'm going to make this subtract, and then inside here I'll have positive terms. So we have 5 over the square root of x cubed. And then subtract 45x squared. And we're going to have multiplied by 3 root x. and plus 3 over x to the power of 7. Okay, so there's our full differentiation completed. If you wanted to simplify that further, of course you could, but I think that obvious simplifications are certainly taken care of in those first couple of steps. All right, so that's how we deal with the product rule in algebraic context. It's pretty simple when you think about it. It's just a pattern to follow. Derivative of the first times the second plus the derivative of the second times the first. Alrighty, but we could also use the product rule in a numerical sense. And these are sort of common questions that you see on test exams and textbooks and all that stuff. So several values of the functions f and g and their derivatives f prime and g prime are given. It says we have to determine h prime of 2 and h prime of 1 if h is the product of f and g. So let's see. If h is the product of f and g, then h prime of x will be f prime times g plus g prime times f. Okay, so in that case, if I want to find h prime of 2, that's the first thing I'm asked for here, I'd need to have f prime of 2 times g of 2 plus g prime at 2 times f of 2. Okay, so we just fill in the numbers from the table. So we're looking where x equals 2 here, and we'll have to use these four numbers. So f prime of 2 we should see is -3. G of 2 is 2, plus g prime of 2 is -4, and f of 2 is 4. So what this gives us all together is -6 minus 16, for a total of -22. So that's the value of h prime at 2. Now we're asked also to come up with h prime of 1. So let's give that a shot. H prime of 1, same pattern, f prime 1, g of 1 plus g prime 1 times f of 1. So we fill in all the numbers there, and we're going to have, let's see, f prime of 1 is, looking at my table where x equals 1 up here, f prime 1 is going to be 5, and g of 1 is 8, and then I add g prime of 1, which is 1, and f of 1, which is -1. So putting all that together, 5 eighths are 40, plus -1, so we have 39 for that one. So we have -22 and 39 for that example. Okay, one more example now. We'll take a look at using a product rule, and this is kind of a numerical example as well, except that we're not given the table of values, we're given a graph. So we want to find p prime 1 and p prime 5 here if p of x is the product of the two functions graphed f and g. So we should know right away that p prime will have to be f prime g, f prime of x times g of x plus g prime of x times f of x, right out. And so therefore p prime 1 we can evaluate, and we're going to have to use our graph to help us out with this, because we'll need to know what's f prime of 1 times g of 1, and then we want g prime of 1 times f of 1. And you might say, well, the graphs we have here are only for f and g. We don't have graphs of the derivative functions. But you'll notice that these are sort of piecewise defined, or maybe some other type absolute value formula for g of x or something. But the idea that we can see here is that since these are piecewise defined functions, and they're all linear bits, then it would be really easy to find the slope on any section of the graph. So we'll just use those slopes from the graph to find out what f prime and g prime are, because remember, the slope of the graph is represented by the derivative. Anyway, excuse me. All right, so let's evaluate this here. So looking at my graph over here, I need to know the slope of both f and g on the line segment where I would find x equals 1. So that's this line segment here. So for f, I'm up 4 units and over 2 units. So I can see that that means my slope would be 2. So f prime of 1 is going to be 2. I'll leave g out for now. And let's get g prime on that same interval. So on the interval that it contains 1, I can see that g goes, let's say between these 2 points, we go over 2 and down 2. So that's a slope of -1 for g on that interval. Then I just need the function values. G of 1 is, at this point, I can see that g has a y coordinate of 1. and f of 1, which I'm going to be interested in now, which I should have written out one there, f of 1 will be equal to 2 if I go up to the height of the function at that point. All right, so putting all that together, I get 2 minus 2, which is 0. So then we need to find p prime of 5. So p prime of 5. So let's see, 1, 2, 3, 4. We're over at the next value that's right here. So we want to get f prime at that point. We want g at that point. We want g prime at that point. And we want f there as well. Okay, so f prime at that point will be the slope of this line segment that sort of starts down here and goes all the way up almost to the end there. I'm going to approximate to say that right here is a pretty close value for g of x on that line segment that I can use to calculate the slope. And I'll use this point right here on f of x to help me calculate that slope. So for f, we have a run of 3 and a rise of -1. So we have minus 1/3 for the slope of f there. And we'll leave out g of 5 for a second. And for the slope of g, I'm over 3, and it looks like I'm up about 2 units. So I'm going to say 2/3 for g of 5 there. Okay. And then I need to find, or sorry, g prime of 5. And then I need to find the values of both f and g at that point. And just looking at the y-coordinates on the curve and over a distance of 5 units for x, I can see that g has a value of 2 and that f has a value of 3. Okay, so since we've got that taken care of, oops, this is supposed to be a 3, isn't it? It didn't look much like a 3 when I wrote it down there. All right, so this will be minus 2/3 plus 2/3 times 3 is just going to be 2. So when I put those together, that's going to be -2/3 plus 6/3, which is minus 4. Sorry, plus 4/3. So positive 4/3 is the value of our derivative of p when x equals 5. All right, so here's a test type question, very similar. It says given the equation of, or sorry, find the equation of the tangent at the point where x equals 2, given the information in the table. So got to first get the value of the derivative, so p prime at 2 will be what we're after first here. So p prime at 2 is going to be f prime at 2, g of 2, plus g prime of 2, f of 2. So in this case, that's going to be 3 times 2 plus 1 by 4. So that's a value of 10 altogether. So then the equation of the tangent line will be y equals, slope is 10 outside of x minus the x coordinate, which is 2. And we have to then add whatever the value of p of 2 is going to be. So p of 2 is just going to be f of 2 by g of 2. And from our table, that'll be 4 times 2, which is 8. So the equation of our tangent line is 10 outside of x minus 2 plus 8 if you write it in slope point form. Okay, so here is the your turn question. So more of those complicated derivatives to use with product rule. So you can take some time and work all those out. And if you want to check your answers now, I'll flip to the solution. So here's the solution for all that stuff with some minor simplifications to make it look not so ugly. All right, and then we'll just highlight some of the key ideas that we talked about here. And there's not really much to highlight. These are algebraic and numerical techniques. So we'll just sort of talk about these quickly. The product rule for differentiating here is given by, as we said many times, f prime g plus g prime f. And we can apply the product rule to differentiate functions that are represented algebraically, which is our most common application, the first one we did. And we can also do that numerically, and numerically using the values that we can take from a graph. So graphically as well, is fair to say. All right, I hope that was helpful, and good luck with your studying.